Okay, so in the last chapter, we looked at the roles of gases in respiration here. Here we're going to kind of take a step backward from that. We're going to look primarily here at the physiology of breathing, as it says, but of course this means really ventilation, of getting a respiratory fluid into contact with a respiratory membrane so we can have the initial gas exchange. And that's all this is about, right? We have to have some kind of a membrane, be it the lining of a lung, be it a gill, whatever, some kind of connection between the respiratory fluid, air, water, whatever, and the transport fluid inside of your body, right? Blood, hemolymph, whatever that happens to be, so that we can have diffusion across that, bringing gases into the internal environment, getting gases out of the internal environment and back into the external, right? Oxygen, carbon dioxide, depending on what we're dealing with. And these respiratory membranes can take multiple different forms, right? So we can have internal, right, like a lung, right, which is a term that we're going to use. Where'd pen go? I know you love my pen at this point. The pulmonary, right? This is of the lung, so something like this, right? Or in the case of something that sticks out of the body, an external respiratory membrane, these are branchial. Not brachial, that's the upper arm, but branchial. So that's these guys. And ultimately, it doesn't really matter, right? Whether it's internal, whether it's external, like a gill. The other thing that we can change about how we bring fluids into contact with these membranes is by either doing the ventilation itself passively, which happens fairly commonly, right? Or maybe something we're a little more familiar with, which is active ventilation, where we actually physically expend energy to move gases past the respiratory membrane. And that certainly, I think, more familiar to all of us. Now, as far as the ventilation itself goes, again, we can go back to something we talked about in the last chapter. The flow can be unidirectional, the flow can be tidal. We can actually have non-directional flow, believe it or not. But we've just got to have some means of bringing a fluid into contact with that membrane. So this is an example of something you're probably familiar with. This is a lung, right? And this is a tidal lung. Not all lungs are tidal, but your lungs certainly are. Where we have inhalation, we breathe in, okay, and we breathe out. And as we breathe in and out, that air that we breathe in is going to mix with stale air that's hanging around inside here, okay? And so we're going to lose some of this partial pressure of oxygen. We're going to go from 100% of the external environment. We mix it with stale air, we might end up with maybe 60%. And so right off the bat, this tidal lung is not particularly efficient because the actual gas, right, that we're going to be using for gas exchange is less oxygen rich than the air that we're walking around in, right? And that becomes important for us because it's this partial pressure, not this one, but this partial pressure that governs how much oxygen we can push into our blood, right? And if we're only at 60%, that means we can only have a blood concentration of somewhere around 60% at best of atmospheric air. However, we do have some means of kind of counteracting that. And it has everything to do with the direction of flow of blood and air. So we can, or water for that matter, if both the fluid, the medium, and our blood travel in the same direction, we have what's called co-current gas exchange. And what this means for us is that as blood passes across the respiratory membrane, the pressure gradient gets smaller and smaller and smaller, right? As we start to remove oxygen from the medium, put it into the blood, we lose pressure here, we gain it there. So by the end of our passageway, right, we're probably only at about 50% of the original partial pressure in the medium, which means we're going to be limited to about 50% of the original partial pressure in our blood, right? Now, we can do better than that, believe it or not. And the way that we're going to do better than that is by having the medium, the air or the water, go in one direction and the blood go in the other. This is called countercurrent gas exchange. And the reason this works for us, right, is that the medium never becomes depleted. Right? There's always some partial pressure. It's lowest at the far end, right, but there's always some pressure there. But when blood comes in, it's been deoxygenated. Pressure is very low, right? So even here, where the pressure in the medium is its lowest, there's still pressure to push gas in, right? And so we can add gas. And here where it's a little bit higher, we can add more gas and add more gas and add more gas. And so we leave, the blood actually last makes contact with the medium when it is most full of oxygen. And so we can get above 50%, right? We can get maybe 75% of the original atmospheric pressure simply by traveling in the opposite direction. With fish that have, well, fish that have gills, with animals that have gills, pretty commonly what we see is instead of countercurrent gas exchange, we get what's called cross-current gas exchange, where the water flows across the gill surface this way, and blood makes several cross-cutting pathways across that pathway, right, across the way of the water. And in doing so, it picks up oxygen from that water at multiple different levels, and all comes together. We net somewhere about, let me say 65% of the original. So it's halfway between countercurrent and co-current in terms of being efficient. When we look at the respiratory membrane itself, the gas exchange membrane, the most important thing for us is size, right? Is body, is area of that membrane. Because the greater the membrane area, the greater the rate of diffusion, right? Remember, diffusion is limited by two things: the thickness of the membrane it has to cross and the surface area across which it can move. So the bigger that surface area, the more diffusion can happen. So obviously, right, when we look at body weight versus respiratory membrane area, there's a positive relationship there, right? But not all animals you see here are on the same line, right? They've all got different trend lines. And the separation in trend lines has to do with activity level, right? So things that are very active and at high metabolic rates, like birds and mammals, have the highest surface area, right, per unit body size. Things that are and are ectothermic, have low basal metabolic rates, or standard metabolic rates, I guess, have for their body weight proportionally smaller respiratory membrane areas. Okay, now obviously you get some weird exceptions in here. Things like yellowfin tuna that have large respiratory membranes because they have high activity levels, but they're really the exception rather than the rule. Now, importantly, this is not lung volume, this is not lung size, okay? Reptiles have big lungs compared to their body size, say in comparison like mammals do, but the surface area within them is relatively small. And we'll see why that is in a little bit. The other thing here that we want to point out, again, remember the important part is that the thickness of that membrane is also very, very important. Right? The thicker it is, the slower diffusion is going to happen. So in things that have high metabolic rates, right, mammals and birds, those membranes are going to be very, very thin. Things that have relatively lower metabolic rates, those membranes are going to be relatively thicker. Now, we've been focusing here a lot on lungs and gills as respiratory membranes, but there's another structure here that is potentially really quite important for certain exchange of gases, and that's the skin. Cutaneous respiration, cutaneous gas exchange is very, very, very important in a lot of different animals, but in particular for amphibians. Okay, so our mud puppies, so you're familiar with this guy if you took comparative with me, big salamanders, smaller salamanders, frogs, tadpoles, all of these guys do, not our eel, all of these guys do a lot of their gas exchange, not through a gill, not through a lung, but through the skin. Things like lungless salamanders obviously do all of their gas exchange through it. Things like hellbenders tend to do a little bit more than the average. When we look at frogs, we find that adult frogs have mostly carbon dioxide respiration through the skin, not so much oxygen. Tadpoles do both. Okay, but in animals that have keratinized skin, so keratin in the skin, so mammals, reptiles, tend to do very little respiration through the skin because they simply can't. Skin is too thick to make it efficient for us. Now, going back to something we talked about with muscles before, central pattern generators. Here with ventilation, again, we have a central pattern generator for this that generates rhythmogenesis. And that's dependent on whether or not we've got what we call continuous breathing or intermittent breathing. Continuous breathing is what you and I do, right? We breathe in, we breathe out, we breathe in, we breathe out. We don't take big pauses in that. The alternative to this is intermittent breathing. Okay, so reptiles do, a lot of reptiles, not every reptile, certainly not every amphibian either, but they do often take a breath and then go through periods of apnea. And all apnea is just a pause in breathing. Right? They don't breathe constantly like you and I do. They breathe a little bit and they take a break. They breathe a little bit and they take a break. Air breathing fish do this also. Okay, so the last thing we'll talk about here, we'll start looking at some methods of ventilation. Here we'll start talking about fish right off the bat, particularly bony fish, okay, in terms of their mechanism. Obviously, they're active ventilators. They're pumping water into their mouths and across their gills. And they do so by separating their head anatomy, the inside of their head, into two big cavities. So we have a mouth cavity here called the buccal cavity. And then behind that, we have the opercular cavity, which is defined by this little flap here called an operculum, which covers their gills. And the idea here is that we're going to bring water in through the mouth and pump it across the gills. Okay, and the gills, within the gills, we're going to have substantial blood flow, so we bring blood into contact with that water and exchange gases that way. So we take a little closer look here. The mouth cavity would be up here. Now we're in the opercular cavity behind, so these are the gills. Right? And the gills themselves are made of these little tiny little branches here called gill filaments that water will flow across and in between. And blood will flow, so water is coming in this way, blood flows this way. Okay, so it's partially countercurrent, partially cross current. And in doing so, right, it picks up oxygen from the water and returns to the body that way. We take a little closer view of one of these little gill filaments. We see that they're extremely complex, with these little secondary lamellae on them as well, blood flowing, again, across the direction of flow, right? Being as efficient as we possibly can. We zoom in a little bit further. Here's these little secondary lamellae again, water flowing between them, blood flowing the opposite direction. This is vitally important, all of this process, all of this anatomy, all of this surface area, because again, remember, water is lousy for oxygen. There's just not a lot in it. And so they need to gather as much as they possibly can, much surface area as they possibly can, as efficient as they possibly can when they do it. The means of pumping in here is what we call a pressure pump, okay, wherein they create negative pressure and then positive pressure and then negative pressure and positive pressure to suck and then push and suck and then push. So the way this works, right, is we're going to start, so here's a simplified version of it, our buccal cavity and our opercular cavity behind it. They're going to open their mouths, right? And do this yourself. You go to the pool, you can't do it now, I say, but go to the pool, open your mouth underwater. Water's going to flood in, right? You're going to create suction, negative pressure. That water fills the oral cavity, right? Then they close the mouth, and as they close the mouth, they create positive pressure, right? Which pushes water into the opercular cavity across the gills, okay? They keep the mouth closed, they slam the operculum shut, create positive pressure in the opercular cavity and force water out the back. Then they start the whole thing over again. Suck water into the mouth, push it into the opercular cavity, push it out of the opercular cavity. Suck water into the mouth, push it behind, push it out. Suck in, push behind, push out. And in doing so, they actually can achieve a fairly high ventilation rate without having to be actively swimming around. As we move forward, we'll talk about other means of ventilation, inclusive of lungs and stuff like that, but that is for another video.